Hello, everyone. Welcome back. This is going to be your fifth lectures on this our lab lecture. So today, what we're going to go over is basically all the basic commands for running a linear regression model that we cover in the class. So I think for most of you guys already learned some of the basic use of R. So we are basically just going to go over the functions that we're going to use for running a linear regression model and also making a plot with the regression lines. And also there are some of the very important outputs like confidence intervals and predictions. So those are the things that we are going to go over today. All right, so first of all, just want to kind of give you a brief idea of why R is actually a very common statistical package to use in the modern days. The reason why it's so popular in both private business world or academic research, it's because there are many individual contributors in the world that it's working on writing a new function for R, and they basically just make it public, open source for people to use. And of course, today, what we are going to use for a linear regression model also is a functions that it's written by those individual contributors in the academic world. All right, so first of all, we are going to use a package called ISLR, which is a package suggested by the textbook. We are going to use all the data package in the two libraries, MASS library and ISLR library. If you haven't installed this package to your machine yet, you would like to run this code called install.packages. Make sure you use the parentheses here and also the double quotes or single quotes for this library name. So once you run this, it will install the package to your machines. As you can see, there is a output right here that telling you, well, it's being successfully unpacked and basically stored in your machines. But once the package is stored on your machines, well, what happens is you need to call them out in order to use it. So for example, we are going to use the two libraries called MASS and ISLR. In order to use this library, you will need to use this command here to call out those packages or the libraries. So let's run this. So we actually run this library. So now we can actually use it in our project. So remember, if you actually don't call this packages out, your machines will not automatically detect it, so you cannot use it in your project. So every time, if you know that you are going to use some of this data sets from these packages, you have to call it out. So even though we have a warning message right here saying that ISLR was built under our versions 3.62, but don't worry, it's going to still work fine because we are just going to use the data sets within the package. All right, so the first data set that we're going to use for our example is the dataset name Boston. So the Boston dataset is basically the data set for the housing prices in Boston. So if you do not know what's in this data set, you can always use the question mark function to basically ask what it is. So again, as you can see, this output right here. So once you click help, it will pull out this window here that tells you, oh, Boston is actually coming from this MASS package. So it's basically giving you the housing value in suburbs of Boston. And here underneath, you can also see all the variables stored in this data set. So for example, CRIM basically represents per capita crime rates by town. INDUS is the proportions of non-retail business per towns. And RM is the average number of rooms per dwelling. And also, you can see all the other variables being stored in this data set. So, unlike calling data sets from your local drive, like pulling out a CSV files or maybe running an Excel files data that's stored to your machines, right? So when you run a project, it's stored in your global environments. When you're actually using a library to call out the data sets, it won't show it in your global environments. So you might actually need to find out like what each variable actually means from this sections here. All right, so well, our objective today is basically to learn how to use linear regression. So the first thing that we would like to do today is to first plot something from the data. So in this case, I would like to find, hey, is there an obvious correlation between the median's selling price, the median values of owner-occupied homes, and the lower status of the population in percentage. So once you use the plot functions and run this two variable, and you will see that there is a plot that giving you the median sales price in Boston's for a single home and also the lower status of the populations on the x-axis here. So by looking at the graph here, it seems like there is a pretty clear trend when the lower status of the population percentage, the ratios here, it's low. That means, well, it's actually not having too many lower status populations. The median price for the housing in those areas tends to be higher. And of course, the other way around, if the lower status of the population's ratio is high, then the overall median housing price in that area tend to be lower. So we would like to use the linear regression model to try to make a predictions here. So what we're going to do here is to use this LM functions. So again, well, if you're not sure about what is a LM functions, well, always try to use the question mark. So in this case, you can actually query, like, what is a linear model, the LM functions. So here, the LM model basically tells you it can be used to carry out a regression single spectrum analysis of variance, analysis of the covariance. So all you need to do basically is to fit a linear model to this function so that it can tell you about the coefficients that we are trying to estimate. Here, very important, every time when you're calling out a function, you have to know how to use it, and the usage basically tells you what you need to pass in to this functions. So you can actually pass in a formula, which we are going to show you in just a minute. And then you have to call the dataset name. And if you have any subset of the data, you can define, and the weights, and also any not available cells in your data can be taking actions for dropping them. Also, there are other parameters that you can pass in, but of course, at this moment, we just want to basically focus on the formula and the data sets that we are going to pass in. If you want to know further more about each of these functions, you can also have all these descriptions of the arguments to pass into these LM functions. All right, so let's give it a try here. Well, what we're going to do here is to have a linear model functions and trying to pass in the formula. The formula will be written in the following way. So as you can see, you have the y variable here, which is the response variable, or the dependent variable, which is the median housing prices. And you're going to use this wiggling dash to define what you want to use for your independent variable after. So the independent variable followed in this formula will be the lower status population ratios, the LSTAT variable. Use the comma to actually separate the second arguments or the parameter you're going to use. So the second parameter you're going to use is to give R an idea which data sets that you're going to use in this model. So you're going to use data equals Boston. So let's run this. As you can see, I actually create a new variable called fit1, right? So this fit1 will store this whole model right here. And this fit1 actually has multiple things that it stores. Of course, you can actually click on this and see what it's being stored here. You can actually see, well, there are coefficients that it's being stored, residuals, the effects, the fitted values, the QR, which is the quadrants, and you can also have the models, the terms, the formula, right? So all this are being stored in this fitted model. Well, to actually look at this output, to be honest, the easiest way probably to do is to use this summary functions. So let's run this summary functions and trying to see what are the variable we want to get out from this fitted model. So once you use the summary functions to call out this linear models, you are going to see outputs here. So this output will tell you everything that we learned in the class, and it will tell you about all the coefficients, the p-values, and also the significant level of each coefficients. So in this case, of course, the most important things to note is the coefficient sections here. So these sections will tell you the betas that we study in the class. So here we have the intercept, which is the beta 0 that we usually describe in the class. For this model, we have a beta 0 equals to 34.55384 positive. And here we also have estimates for this LSTAT estimates, which is the beta 1 that go with the variables. So this beta 1 is a negative number, and the value of this is negative 0.95005. And you can also see all this standard error and t-value that we cover in the class. But again, the most important things that you need to know in this output section is the p-values. So the p-value of each coefficient will tell you how significant they are in this model. If it's a very, very extremely small number, let's, for example, taking a case, you only accept the statistical significant level at 5%. If any number is smaller than 0.05, then you will believe that this coefficient is most likely correct. And if this p-value is actually higher than 0.05, let's say 0.15, then it's basically reject the null, fail to reject the null hypothesis, saying that the coefficient is not statistically significant. So either one way or the other, well, you are always trying to look for a small number, okay, in this p-values output. And here you can see what the stars are basically represent in this output screen right here. The 3 star basically means anything that close to 0. So if you have a double star, that means, well, it's significant at 0.1% level. If it's 1 star, then it's basically significant at 10%, 1% level. And we also have the residuals. So as you can see here, we have the residual standard error, which is 6.216, and we will cover that in the class later. And the most important things that you have to note at this point is this Rsquare. So this Rsquare basically gives you an idea how great this model is overall. So this model basically explained 54.41% of the variations of housing prices by using the variable LSTAT. You also want to check the Ftest statistic value. So if the Ftest tells you that we have a p-value extremely small, again, it basically gives you an idea that this overall model is statistically significant. So at this point, obviously, the single test for the coefficients, beta 0 and beta 1, already proven that this model is statistically significant. But if you do have multiple variable case, then the F statistic will be much more important to look at because it actually tests the overall significant level for all the beta that we put into the models. So again, you are looking for an extreme small value in this test so that you can actually reject the null hypothesis that's saying the model is statistically significant. All right, so at this point, obviously, those are the things that you can simply do, right? So without much of a problems. Now, the next thing that we want to do is to plot the regression lines and visualize the fitted lines in the graph that we plot earlier. So remember, we actually plot the data on a single graph. So what we want to do now is to use what we call A/B line functions to actually plot the regression lines by putting in the fitted model into these functions. So in this case, I'm going to plot a A/B line right here by using the fitted models, fitted 1. And we are going to give a color for this line, which is red. So let's see what it does. As you can see, we're actually getting the plots again. So we have all the data points here. And now we have a single lines, the red lines here that pass through most of the data points. So this line right here basically is the regression line that we use to make our predictions of the y value. So we are basically making assumptions here. The x-axis, the LSTAT variable, has a linear relationship with the median housing price in Boston. So that's why this fitted lines is the one that we estimate from our models. Well, if you want to actually basically give a name, right, to this model, so you can actually try to use the names functions here. So let's see what it does. So if you actually use the names function, it will give you all the variables that it's being stored in this fitted one summary. As you can see, the first thing stored in this fitted model is the coefficients, and then the residuals, and then the effects, the rank, the fitted value, and so on. So it's similar to when you're clicking on this button right here to list all 12 store values in this model. So you can actually use the name functions to basically call all the things that it's being stored in this fitted model. You can also take the convenience of this confident intervals functions, right? So the CONFINT functions, so the confident intervals. You can actually get the confident interval for this fitted models like the following. As you can see, you can actually ask the questions. What is the confident interval for the beta 0? Right, so what is the value of beta 0 will be rejecting the null hypothesis within, well, in this case, you can see, well, 2.5%, 97.5%. That means, well, this is a two-tail confident interval, 2.5% on the left, 2.5% on the right. So this is a total of 5% significant level confident interval. And this here, it's basically the confident interval for the beta 1. Right? So again, it's 5% significant levels confident intervals. This is the variations that we accept for our estimations for the two estimated coefficients. Well, if you want to actually get a more strengthened confident interval, let's say, well, you want to actually have a 99% significant levels. So you want to have only just 0.5% on one side, 0.5% on the other side of the intervals. Then you can actually use the confident interval functions by putting in the fitted models. And again, you can define another arguments here by setting the level. So in this case, well, we are going to basically store the confident intervals for this model at a 99% significant level. Run this. As you can see, well, it store the x value here for the intervals, and let's print them out. All right, so comparing to the previous, as you can see, previous we have 2.5% on the left-hand side, and now we have only 0.5% on the left-hand side tail. Previously, we have 2.5% on the right hand, and now we have only 0.5% on the right-hand tail. And this is the interval for the value of beta 0, and this is the intervals for the beta 1 values. So you can actually utilize this to test your models as long as those values does not give you a 0 within. Let's say, well, it's not a value within -1 to +1. Then the model suggests that the beta should not have a high chance to fall into a value of 0. So that means the beta actually is statistically significant. Again, if you have questions about the confident interval, you can always try to ask the questions, right? How to use it. As you can see, you can actually pass in the subjects, which is usually the fitted models that we use. And we can also define the level of confidence. It's basically, as you can see in the previous example here, it's default by 2.5% or 5% overall significant levels for the two-tailed test in this case. Now, what we try to do is to make a predictions. Remember, any statistical model that we build, it's basically have this one key function, which is building the predictions, right, for our model. So in this case, you can actually try to use this predict functions here, and we are going to run this model. So prediction functions. So the model prediction functions actually allows you to pass in the model and trying to run the models and get a predictions from the model. So in this case, well, obviously this does not give you a lot of details on how to use it. So I'm just going to use our example here to define. So in this case, for using this prediction functions, first we need to pass in is the model that we save, which is fitted 1. And then you can also define which data sets or subset of the data you would like to use to make your predictions. So which rows of the variable LSTAT variables that you want to use. You can actually select a very small subset of the data to pass into this model. So the overall idea is to basically define what is the value of LSTAT to put into this predictions so that we can actually get the dependent variable, the response variable from our predictions. So in this case, we are passing in the variables from the data frames, which actually take the dimensions of this. 5, 10, 15. And we are going to define the interval for our predictions. And we are basically set the confidence intervals and at a level of 0.99%, so 1% significance. So let's see what it returns. So as you can see, we return 3 columns of number. So we are using the values of LSTAT from row 5, row 10, and row 15 to make a predictions of the housing prices. As you can see, when we're using row 5 value, we have the fitted value here, which is equal to 29.80359. So this is the median housing values if given the value of LSTAT, the lower status population ratio percentage, from the 5th positions of the columns. And if you're using another value from the LSTAT columns, and we have another fitted values. So this is the return fitted value from the model, so 25.05335, which is the median housing price if given the value from this positions of the columns. And as you can see, we can also see the lower bounds of these predictions. Remember, we set the confidence interval for these predictions at 1% significant level. So this is the lower bound of the value. So there is only 1% of a chance that you will be wrong if the value actually go below 28.75578. And also 1% of a chance that you will be wrong if the value of the predictions actually go above 30.85141. Well, you can see the upper bound and lower bound, it's also reported for other value here. So that it gives you a convenience to always get the confidence intervals by using the predict functions here. And now we're going to explore something that's more interesting. So last time we basically covered how we can actually use multiple variables in the regression model. So this time we want to actually change our specifications of the model. So instead of just using LSTAT, the lower status population ratios, we want to actually add another variable. So this time we want to also add the age. So the age, I think the average age of the populations in this area. And we are going to define a data set again from Boston. So let's see the fit. So we store this into fit2, and it will save all the 12 parameters into this fit. And let's get the summary. So as you can see, this output is similar to the previous. But the only difference here is we're now adding one more variable, the independent variable into our functions. So this linear model actually has an intercept, which is 33.2276, a beta 1, negative 1.03207, and a beta 2 that go with the variable age, which has a positive coefficient 0.03454. Again, the first thing you should note is the p-value. So as you can see, well, the p-value is still extremely small. So it's 0.00491. So that means it's 0.4% of a chance that you will get wrong of this variable. So it's extremely, extremely small. You can also see, well, the R-squared value here. So the R-square in this case is 0.5513 for this model. And in the class, we are going to basically explain what is the adjusted R-square. So whenever you have a multiple variable regression model, it's usually strongly suggest to use the adjusted R-square instead of the regular R-square value. So in this case, I take the adjusted R-square value and say, well, this model actually explains 54.95% of the variations of housing prices by using the variable LS, TAT, and age in this model. When we look at the F statistics, again, the p-value is extremely small, so that's proven, again, the model itself is statistically significant. So all of these beta estimates should not be zero in our models. All right, so now if we want to actually use all our variables in the data sets to estimate, right, to make a predictions of the median housing prices in this data sets, well, you might actually want to ask the question, hey, does it mean that we have to add all the stuff into these functions? So we have to type every single variable out? To be honest, there is a very convenient way to actually call out everything from the tables or from the data sets. This is basically covered in, well, very commonly used in data science or computer science. So in this case, we can actually look at the Fit3 model. We are going to use, again, the linear model. We are passing in the independent variable, which is the median housing price. And we use the wiggling line. And what we define here is a dot. So in most of the computer science language, a dot basically means all of them. So when we're passing in a dot into this model, we basically define we want to pass in all the variables from the data sets to this model for our estimates. Only except this already defined variable, of course. And we are going to, again, call the data set, right, which is Boston's. So let's see what's going on. So we have the Fit3. And let's print the summary. Ooh, wow, this is very interesting. So now what we see here, it's an output that it's very, very big. You can see, well, you have so many variables in our model now. Some of them are significant, some of them are not significant. And how do I know? Very simple. I just look at the stars. So as you can see, well, there are beta 0 here, beta 1, beta 2, beta 3, beta 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 variables, it's being passed into these functions. And this one right here without the star, age, is not statistically significant. And as well as this one, the INDUS variable, it's not statistically significant. So in the class, we are going to discuss more about the model selections, how we are going to pick the right specifications of the models. But for now, well, obviously, those two variables are the ones that we suppose to drop from the model to try to make a better fit to the model. But one thing that's very important for you guys to note, when you look at the R-square, in this case, the adjusted R-square, it's much, much higher than the previous model. And it actually explains 73.38% of the variations of the housing prices by using all the variables in our data sets. Well, also, the F statistic tell us, well, this model is statistically significant. The whole model is statistically significant. And not every single beta in our model is zero. Right? So at least one of the beta is significant, then the p-value will be extremely small. So in this case, obviously, there are so many variables here, they are statistically significant. So it's proven, again, the F statistic is correct. All right, so let's say, well, we don't want to pass in everything, right? And obviously, well, INDUS and also age are the two that we want to drop. So what can we do to our models? So in this case, we're going to try Fit4 right here by passing in, again, the response variable, the median price. We are going to pass in every single variable from our data sets. And now we're going to utilize this negative signs. So we're going to say, well, subtract age and subtract INDUS indus. and we're going to pass in the dataset Boston again. So in this case, well, we can actually use the negative sign to take out or drops some of the variables that we have in the dataset by using the dot, which is passing in all except for this two. Let's run this and see what's going on. So here's a summary. So obviously, the good news to us is every single beta that we estimate in this model are statistically significant at some level. Some are at a lower level, some are at a higher level. But at least every single one of them are statistically significant at least 0.001. That means, well, 0.1% of a chance that you will be wrong. And adjusted Rsquare also tell us that the models explains 73.48% of the variations of the median housing prices in Boston. Well, comparing to the previous, so 73.48, and here, even though we're putting in more variable into the previous model, as you can see, if we actually include something that is not statistically significant, you might actually get the R-square or the adjusted R-square much lower value in this case. Again, check the F statistics. The p-value is extremely small. That also, again, proven that the whole model is statistically significant. All right, so at this point, well, we try several ways to run the functions, and I'm trying to use the linear model to make a fit for the model. Well, let's talk about how we can actually make transformations in the next lecture, so you can actually use it to make some adjustment to your models with the needs of changing the models. All right, so I will talk to you guys next time. So